This is the first video for the Chapter 7 notes. Chapter 7 is on estimating parameters and determining sample size. Section 7.1 is estimating a population proportion. So the section presents methods for using the sample proportion to make an inference about a value of a corresponding population proportion. We have what's called a point estimate. Is a single value. It's used to estimate a population's parameter, and the parameters that we're going to be using are proportions and means, and so we'll be using p hat and x bar as our point estimates. So p hat is for the proportion and x bar would be for the mean. So the sample proportion p hat is the best point estimate and it's unbiased of the population proportion p. Next topic here is confidence intervals, or an interval estimator, is a range of values used to estimate a true value of a population parameter. We have confidence level, and this is the probability 1 minus alpha, such as 0.95 or 95%, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Alpha is called the degree of confidence or the confidence coefficient. An example of a correct interpretation of a confidence interval would be something along the lines of we are 95% confident that the interval from 0.405 to 0.495 actually does contain the true value of the population proportion P. So we actually use confidence intervals in just everyday life. A lot of times after you take an exam, you might say something along the lines of, I feel pretty confident that I passed. So all we're going to be doing for our course is kind of extending upon that. So what do you mean by I passed? Do you think it's going to be between what value and what value? A 70 and a 90%? And then also placing a level of confidence, because we could always still be wrong. There's errors that occur. And so for us, you might not be 100% confident that you passed, but you might be like 95% confident or 90% confident. So we're going to place this level of confidence on that also. So the example right below says a USA Today Gallup poll asked 1,006 adult Americans how much it would bother them to stay on a room that's on the 13th floor in a hotel. Interestingly, 13% said it would bother them. The margin of error was 3 percentage points with a 95% confidence. Which of the following represents a reasonable interpretation of the survey results? For those not reasonable, explain the flaw. Part A, we are between 92 and 98% confident that 13% of adult Americans would be bothered to stay in a room on the 13th floor. So this one is not correct. And the reason is because it is stated in the problem that we are 95% confident, and this confidence level does not change. So we cannot change our confidence level. We'll say can't vary. And so B says, in 95% of the samples of adult Americans, the proportion who would be bothered to stay in the room on the 13th floor is between 0.10 and 0.16. So this one for us is also not correct. And for this one, it is suggesting that the interval sets the standard for all other intervals. So if we were to sample this maybe in another area, they might not have the same beliefs and the same problem with staying on the 13th floor. So this one suggests that this interval sets the standard for all other intervals. Part C says, we are 95% confident that 13% of adult Americans would be bothered to stay in a room on the 13th floor. Part C is also not correct. And the reason why is that there's no interval given. So no interval has been provided. about the population. So D says we are 95% confident that the proportion of adult Americans who would be bothered to stay in a room on the 13th floor is between 0.10 and 0.16, and this is correct. And so looking at those numbers with the 0.10 and the 0.16, and this is because, again, 13% said it would bother them to stay on there, and we have what's called a margin of error of 3 percentage points. And so we have 13%. And so if you add that 3 percentage points and subtract the 3 percentage points, we're going to get that confidence interval. And so 13 plus the 3 would be 16%, and then subtracting the 3 would be 10%. And so your interval is between 10% and 16%, which as decimals is 0.10 and 0.16. Right below it says a confidence level of 95% tells us that the process we are using should be, in the long run, result in a confidence interval limits that contain the true population proportion 95% of the time. Suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. Then our sample proportion is denoted p hat equals x over n, where x is the number of individuals in the sample with a specific characteristic. The sample proportion p hat is a statistic that estimates the population proportion p. The example on the next page says, in a town of 500 households, 220 have a dog. The population proportion of dog owners in the town, expressed as a decimal, is p hat equals, and so we're going to divide 220 divided by 500. So the number of people with that characteristic, which is owning a dog, divided by the total in our sample. And this works out to being 0.44 as a decimal. Note that a second survey of 500 households would likely have a different estimate of the proportion of households that own a dog. So if we were to survey a different area, maybe that's not so common to have a dog, or maybe even another area where it's even more likely to own a dog. Because the value of p hat varies from sample to sample, it's a random variable and has a probability distribution. To get a sense of the shape, center, and spread of the sampling distribution of p hat, we can obtain a random sample of data over and over again, get a list of the sample proportions, create a histogram of the sample proportions to gain an idea of the shape, calculate the mean, gives us an idea of the center of the distribution, and calculate the standard deviation will give us an idea of the spread of the distribution. So the next thing that we have are called critical values. And a critical value is a number on the borderline separating the sample statistics that are significantly high or significantly low from those that are not significant. And so again, remember that significantly high is going to be that top part. So this would be our significantly high. And significantly low would be that bottom cutoff. And then anything in the middle is not significant. For example, a 95% level of confidence, or alpha equals 0.05, implies that 100 different confidence intervals are constructed, each based on a different sample from the same population. Then we expect 95 of the intervals to include the parameter and 5 not to include the parameter. 95% of the time the parameter will be included in the interval. And so right here we can see this, 95%. And you'll notice that right here we have these little 2.5. And to get this, you would do alpha divided by 2 because it gets split. So with confidence intervals, it's always going to be split. And alpha divided by 2 is just going to have to go in each of those little tails. A 95% level of confidence does not tell us that 95% probability the parameter lies between the lower and the upper bounds. Right below, we have common confidence levels and corresponding critical values. So this is a great table to have handy when you're doing your homework or your quizzes or your exams. And the reason why is because these are the most commonly used confidence levels of 90%, 95%, and 99%. And you will notice that these critical values over here on the far right are going to be used also throughout this whole entire chapter, and then you will also see them in other chapters. So sometimes we have problems that are not going to have the confidence levels that are listed on here. So the example right below says calculate the critical value for a 98% confidence level in round 3 decimal places. So 98% is not on my table, but you can definitely add more to your table so you have these values. But we're going to go ahead and calculate this. Find our normal curve. And we do know that our critical values are z values, which means that our mean is going to be 0 and our standard deviation is going to be 1. And so from here, I'm going to have two cutoffs that are going to be labeled Z1 and Z2. And this way we are 98% confident. I'm going to write as a decimal. This is 0.98. And then the total area under the curve we saw before is 1. And so 1 minus 0.98 is 0.02, and this is how much area that we have in each of these little tails, but that has to be evenly split, so I'm going to divide it by 2, which is 0.01. So each of these tails has a very little area, 0.01 in each of those, and again, if you add up all of those values, you should get 1 as your total area under the curve. So to calculate our value for Z1, we have to use inverse norm. Area to the left is 0.01. Our mean is 0 and our standard deviation is 1. Z2 is also calculated by using inverse norm. This time area to the left though of Z2 is 0.98 plus the 0.01, which works out to being 0.99 with a mean of 0, standard deviation of 1. On the graphing calculator, to calculate Z1, we need to go to second vars, inverse norm, area to the left is 0.01, comma, our mean is 0, standard deviation is 1, close your parentheses, select enter, and we get our Z value. In order to calculate Z2, same idea, second vars, and then inverse norm, and our area to the left for this one is 0.99. Mean is 0, standard deviation is 1. Close your parentheses, select enter, and we get our Z value for Z2. From the graphing calculator, we get Z1 is negative 2.326 and Z2 is positive 2.326. And so we get two values that are identical except for one is positive and one is negative, again because of that symmetry. But the positive one is going to be our critical value. And so this is what we would have as our critical value for a 98% confidence level. At the top of the next page, it says requirements for creating a confidence interval estimate of a population proportion P. And so this is what we would have to check to verify that we can actually find a confidence interval. So the first thing is going to be that the sample is a simple random sample, and 2 says conditions for the binomial distribution are satisfied. And for 3, we're going to have to verify that n times p and n times q are both greater than or equal to 5. So the higher level of confidence leads to a wider interval and a larger margin of error. Margin of error E is the maximum likely amount of an error between the sample proportion p hat and the population proportion p. It's also called the maximum error of the estimate and can be found by, we have a couple different formulas listed here depending on what you're given. So you'll notice that the first equation has z alpha over 2 times the square root of p hat times parentheses 1 minus p hat divided by n. And so z alpha over 2, this value, is the values that are those critical values that are also on the bottom of page 2. And then you would also have p hat. The other equation that you have to the right is using the upper bound and the lower bound of your confidence interval. So there's a few notes underneath this that says that a confidence interval about the population proportion is a form. And so there's 3 different ways we can actually write our confidence interval, and we'll look at all 3 of those in a moment. 2 says the point estimate p hat is the midpoint of the upper and the lower bound. And 3 says the margin of error E is the difference between the point estimate and the lower bound. So we're going to add a few formulas here that need to be written down in your notes. And this is going to be the p hat. You can add E and subtract E. And this is going to give us our upper bound and our lower bound. And then to get our p hat value, we can take our upper bound plus our lower bound and divide this by 2. This is also called the midpoint. And then for my open math, sometimes she's going to ask for a trilinear inequality. And she'll have it written with p hat and e, asking for those values, and then it will also be given with some blanks in here where you would have to fill them in. And so just like what we saw up above, this would be p hat plus our margin of error, and the other way would be p hat minus our margin of error. This can be also written as, p hat plus or minus e, or as p hat minus e, comma p hat plus e. So these are the 3 different ways that this will be written. The last one is how the calculator will give us our answers, and so a lot of students will typically do this on any kind of written assignment. So the example right below says express the confidence interval using the form p hat plus or minus e round 3 decimal places. Says the confidence interval for the proportion of red M&Ms is, and they give us a value here, and so it's p is going to be between 0.0434 and 0.2170. So our p hat, using the formula up above, is our upper bound plus our lower bound. So this is going to be 0.0434 plus 0.2170 divided by 2. When you work this out on your calculator, you get 0.130. And then in order to find E, our margin of error, we are going to use the formula that's up at the top that we have starred already. And since we have the upper and lower bound, and so this one says your upper bound minus your lower bound divided by 2. So our upper bound here is 0.2170 minus 0.0434 divided by 2. When we work this out, we get 0.087. And so to write our answer, I'm going to write as p hat plus or minus e. And so this is going to be p hat, which was 0.130 plus or minus e. And for this problem, we got e as 0.087. Right below, we see constructing a confidence interval for our population proportion using our graphing calculator. And so with this is for proportions and not for means. We'll get to means in the next video. So if step 1 is to compute p hat, this is going to be x divided by n. Step 2, you need to verify that it's a simple random sample, the binomial distribution is satisfied, and n times p and n times q are both greater than or equal to 5. So these are the requirements that you have to check. So that's what you would have to check. Step 3, you're going to go to Stat, find your Stat button, scroll right to Test, and then find one prop z int. You're going to enter in your x and your n value, your confidence level, which they call C-level, and then highlight calculate and select enter. The answer is going to give you your lower bound, comma, your upper bound. And then one of the big things here that you need to do is interpret your results. And so interpreting again means to talk about. So at the top of the next page, we have an example that says, in a study of the accuracy of fast food drive-thru orders, McDonald's had 33 orders that were not accurate among 362 orders observed. And based on, and it has the study given there, round 4 decimal places. So part A says find the best point estimate of the population proportion P. And the point estimate is going to be P hat. And the total number of drive-thru orders that were incorrect is 33 out of the total number of drive-thru orders that were observed, and this is 362. Dividing this on our calculator and rounding 4 decimal places, we get 0.0912. Part B says, identify the values of the margin of error E for a 95% confidence interval. So for this problem, we had two equations for E on the previous page. One was using the upper bound and lower bound, which I do not have at this time, but the first equation that was listed there is Z alpha over 2 times the square root of P hat times 1 minus P hat divided by N. And we have P hat, we just calculated that up above, and we know N is 362 since that was our sample size. So now we have to talk about Z alpha over 2. So we are dealing with a 95% confidence interval. And so if you look back on page 2, so looking at page 2, where we have 95% confidence interval, you'll notice that our Z alpha over 2 value is 1.960. So I'm going to go ahead and take that number and use that as my Z alpha over 2 value. So again, from page 2, we have Z alpha over 2 is 1.960 times the square root of 0.0912 times parentheses 1 minus 0.0912, close parentheses, and divided by 362. From the calculator, you get 0.0297. Part C says to construct a 95% confidence interval. And so with this, we actually have P hat and E. You can also use your graphing calculator to do this, but I'm going to just go ahead and use the values that we have already. And this is going to be that's between P hat plus E and P hat minus E. And we know P hat is 0.0912 minus E, which is 0.0297. And then adding them, we get 0.0912 plus 0.0297. Simplifying this, we get 0.0615. And our upper bound, which is going to be 0.1209. So that's our confidence interval. Part D says to write a statement that correctly interprets our confidence interval. And so we're going to say about 95% of these confidence intervals will contain the true proportion of not accurate McDonald's orders and 5% will not. So a couple things to discuss here when you're writing your interpretations is this 95% is matching to the confidence interval that we had up above, and the 5% would be 100 minus the 95%, and that's going to give us that leftover percentage, which is 5%. The other thing too is to make sure that you do write about exactly what it is that the problem's talking about, because every single problem is going to be different. Right below, it says, as the sample size increases, the result is a narrower confidence interval and the margin of error decreases. And we have a couple of formulas that we do need to know. The box says sample size N needed for estimating the population proportion P. So when the estimate P hat is known, so this is where you would have had a previous study done and you already know something about that data. And something to note here is that Q hat is equal to 1 minus P hat. And so we have the Z alpha over 2, which is again that value that was on page 2 from the critical values, or you would have to calculate it on your own like we did in the example below. P hat, which is that sample proportion, Q hat, which is 1 minus P hat, and then our margin of error squared. And then you round up to the next integer. So it always needs to be a whole number, and we are always rounding up. This is the only time that we do this type of rounding is with sample size. The next one says when no estimate P hat is known. So this would be something like it's a new thing and we're doing a new study on it. So like when COVID started, that was a new disease that we had to study, and they had no prior estimates on anything in terms of COVID. So for this one, we have z alpha over 2 squared times 0.25 divided by e squared, and you'll notice this time there is no p hat because we have no prior estimate. So again, for this one, you're rounding up to the next whole integer. So the example right below says, find the sample size needed to estimate the percentage of California residents who are left-handed. Use a margin of error of 3 percentage points and use a confidence level of 99%. So it tells us our confidence level, and it also tells us our margin of error is 3 percentage points. So this means that E is equal to 3%, and as a decimal, this would be 0.03. So part A says, assuming that nothing's known about the percentage of left-handed residents in California. So since no prior estimate's known, that means we're going to be using that second equation, which is z alpha over 2 squared times 0.25 divided by e squared. And so for this, I need to get my z alpha over 2. So looking at our table on the bottom of page 2 with a 99% confidence level, you can see that our critical value, the far right column, is going to be 2.576. So our z alpha over 2 value is 2.576 squared times 0.25 divided by e, which we have as 0.03 squared. When working this out on our calculator, we get 1,843.27, but remember we always round up to a whole number, and so this is going to be 1,844 people that we will have to survey. Part B says, assume that based on the prior estimate, about 10% of Californians are left-handed. So because we're given this information, we know p hat is 10%, or written as a decimal is 0.10. So since we have a prior estimate, we're going to use that other equation, which is n equals z alpha over 2 squared times p hat times q hat, all divided by e squared. And we already looked at the table above and got the z alpha over 2 for our confidence interval to be 2.576. And we're going to square this. P hat is 0.10. Q hat, again, is 1 minus p hat. You can also write this as 0.90 divided by E, which again is at 3 percentage points, written as a decimal. So substituting this all in on your calculator. On the graphing calculator, I'm going to simplify the numerator first, which we have 2.576 squared. And we have an x squared button that we can use for that. And then this is times 0.10, and then times, and I'm going to subtract that 1 minus 0.10, and I get 0.90. Enter, and that's my numerator. I am then going to divide this by the denominator, which was e squared. So select the division button on your calculator, and we're going to divide by, and it is parentheses 0.03 close parentheses squared, and then select enter, and we get our number of people that we need to sample. Remember that we do need to round this value up. We get an answer of 663.58, and again we need to round up, and so this is going to equal 664 people. So in part A, where we had no estimate, we needed to survey a lot more people to be that confident, to be 99% confident, whereas for part B, we had to survey less people. The reason why is because we had p hat, which means we already had collected information that we were able to use.